Okay, so lesson 37, power to the home. We will learn how AC current is used in the home. Now, this is the next topic, and it's the final topic for electricity. Now, I'm not sure if you guys might not get this, but what we're trying to do is we're trying to do most of the topics are broken up into smaller sections. Thermodynamics is broken up into two topics: thermodynamic basics of thermodynamics, and then we talked about global warming. Electricity is broken up into three: the basics of electricity, so the physics of electricity. Then we talked about circuits, which was the whole big topic we just did was. And the last topic is about electrical safety. So how can we make sure that we are being safe in our homes? What devices exist to make sure that we don't get an electric shock and die every second that we plug something in? So this is what the point of this topic is. Let's discuss, well, how are we safe? I also like this topic because it gives you guys an understanding of, okay, how do circuits work in the home? Because ultimately that's where you guys have the most experience with electricity, is around your home. So today we're going to talk about, well, how do we get power to the home? How do we get electricity in the house? And to talk about that, we're going to talk about AC current, and we're also going to talk about well, what's the process of it coming into the home. So we're going to start off by, I want to show you guys this. These are all the topics. So last night I was like, okay, remember, sure, this is the first time I've ever taught this topic before. So because this is the first time I've ever taught it, I don't really know the best process to go about it. So what I did was I just wrote down, these are all the things that you guys need to learn by the end of this topic. You guys need to be able to tell me each of these things. You guys might think that's a lot, but actually, to be honest with you, we're going to be finished with this topic in about a week. I predict by the end of Tuesday's lesson next week, we should be finished. So I then group those topics into 4 lessons. We've got the first lesson, which is today. We've got a second lesson, a third lesson, and a fourth lesson. And these two are shorter, so I reckon we can probably do them in a single period. But this one's pretty big. It's got a lot of information, so I reckon we're going to need a double for it. So that was my planning. I just thought it might be good to show you guys how I came to this thing. So, and the next thing I want to tell you guys is this: the PowerPoint for this is done. These two are not. These 3 are not done. So I'm going to be making those during the week. So if you open up this PowerPoint now, you'll see after this lesson, it's a big mess of stuff. And that's because I haven't organized it into nice little lessons yet. I will, but you won't be able to open this PowerPoint because I haven't made it available yet. I will make this PowerPoint available to you guys on the classroom, on that folder, so you guys can click on it. I know that I'm saying that for Arn because I know Arn likes to follow along. I know everyone does, but I always think about Arn when I think about it, because he always asks me, where is the PowerPoint? I'm like, don't worry, Arn, I haven't forgotten. I will put it up. I just was a bit busy last night making this. Let's start the topic with the power coming into the house. The first place the power goes to, the electricity goes to when it comes to your house, is a switchboard. Now you guys should all have a switchboard somewhere in your house, probably near the front, usually in a box, like it's a big long wooden, or sometimes they used to be wooden. Now it depends how old your house is, but they're usually now a metal enclosure. And this is where electricity comes in your house. It starts off with a switchboard. The switchboard divides the electricity into different parallel circuits. So if you imagine your electricity comes streaming in, it goes into a switchboard, and then your switchboard then splits it into different currents. Sometimes these currents are called rings. And these different current circuits, one of them might be for lights. One of them might be for your appliances. One of them might be for like a stove or an oven. One of them might be for, you know, maybe it's for your pool, because maybe your pool has a special cleaner in it or something like that. But it will split them into different, what they call rings. At least I'm pretty sure they're called rings. The reason that they have different, they do this is because, of course, if one of them shuts down, let's just say you have an issue with one of your power points, and so therefore this whole ring here gets closed, you don't want your lights to turn off. So they put them on different parallel circuits. It also means that there is another advantage as well. It means that, like, okay, let's just say your oven, because you've got an induction oven, requires a high voltage, then you can sort of manipulate each of these to have different voltages. Before we get to the switchboard, though, we have to go through a meter. Now, the meter, all the meter does is the meter just says how much voltage, how much current electricity you've used. The main purpose of that is so that your electricity provider, AGL, or whoever you're with, Origin Energy, can charge you money. So what they do is a man comes out to your house and looks at the meter and then writes it down. Nowadays, though, because we have digital meters, what they can do instead is, I think they can just sort of like they can just collect that information without actually necessarily going to the premise. But I'm not actually 100% sure how the meter goes. There was a big controversy, I remember, because they only switched over to digital meters about 4 years ago or so, 4 or 5 years ago, and it was a big bit of a controversy. It's like, oh, you know, now people can spy on me, you know, this usual sort of conspiracy theory. There are, inside the circuit, there are circuit breakers. These act as safety devices and add a large switch to turn off and on all power. Let's grab a look at this actual one here. You guys may have seen something like this in the room that we teach in S3 that I've sometimes fiddled with. Yeah, that's just a switchboard. On the left here, we've got the main switch. And that sort of controls all of the current that goes into the house. We can turn it on and off. Whereas these are the individual circuit breakers, the individual loops. So if you think each of these controls one of these loops. This one's got a lot of them, and your house might have a lot of them. You may, this might be a business, so that might be why there are more loops. But yeah, if you like just have lights and appliances, you might only have 1 or 2. But if you've got lights, you've got appliances, you've got a fridge, you've got a pool, you've got, you know, a stove, you've got a pool with some other random thing in your house. Maybe your home theater is so big that it needs its own separate circuit. Yeah, well, you're going to have more than one switch. So all power starts off going into the switchboard, and this is also going to be the place where a lot of our safety is going to be occurring is here, because the best way to be safe is just to cut the whole power to the house. Sometimes you'll find if the power gets cut to the house, you have to come back out and switch the power back on by flicking those switches up. I remember the first time I did that, my father was an electrician, so he was able to say, yeah, it's okay. So I think we had this really bad, like, you know, something, I think one of like the toasters exploded or something, because, you know, maybe someone put Batman in the toaster once. It killed the toaster. When the toaster died, it shorted out the power to the whole house. So we had to unplug the toaster and then turn on the switches individually. Sometimes after a power outage, you may also see this happen. So you have to switch on the power individually. But yeah, this is what a switchboard is. It's a little bit like, so if you think about a switchboard as like the main part of a really more complex circuit. So these circuits are a little bit more complex than your classic series parallel circuits that we've been talking about. But there are some factors here that are very, you know, they're very similar. So as I said to you guys, the main switchboard breaks out the electricity into different circuits. Here's some examples, right? You've got lighting, power. So you might have two things for power. So because like, I mean, think about it, your lighting doesn't require that much voltage, but like if you've got like a computer plugged in, a microwave plugged in, a TV plugged in, an Xbox plugged in, you're gonna maybe need more than one power circuit. Maybe one of them serves downstairs, one of them services upstairs, I'm not sure. A stove and a hot water heater. Hot water heater, didn't think about that. You know, a lot of people have electric hot water heaters nowadays. So that might be, you might have an electric heater, like electric heating. So that might be, for example, I think we've got electric, we don't have electric heating, we have gas heating, but the big fan that blows everything around, you better believe that that's electric. So let's follow one of these circuits. We've got this lighting circuit here, and that has this big red thing, and that red line represents the active wire. Okay, and this is a parallel to the power circuits and the stove. They're all parallel circuits. Each circuit has parallel components, so they can all be switched off and on independently. These have, the lights are not connected in series, they're connected in parallel. Why? Because then if I switch this light off, it doesn't switch off all the other lights. It also means that if this light, let's just say this light globe dies, you know, if that light globe dies, it doesn't switch off power to all the other light globes because they're all connected in parallel. That's why we really like parallel circuits, because it means that we can split all the voltages. Now you'll notice that you've got, coming out of this wire, you have a blue wire. Now this blue wire goes back to the battery, back to the in this case it goes back to the neutral and goes back out to, you know, back out to the rest of the world. And so that's actually the complete circuit. We've got a negative, an active, which is going to be like our positive wire, and a neutral, which is going to be like our negative wire. But you guys might see there's an extra wire going on here. That extra wire that's going on here, we refer to as a ground wire. We're actually going to talk about this a lot more in the next lesson. I just wanted to maybe touch on it now because it's in this picture. This ground wire here follows the same path as the neutral wire, except it goes to something called ground. And we're going to talk about this a little bit more next lesson. The idea is it's a safety component. If something goes wrong, you want to make sure that that electricity has somewhere to go, somewhere to get out of the house. And ground wire is a way that you can get out of your house, out of your wherever you are. Now we don't normally use fuses anymore, but we usually now use circuit breakers. But back in the day, you would use fuses. In fact, old houses still probably have fuses. And if you've ever played like an indie horror game, they're like, oh, you've got to find the fuses so you can turn the lights on without getting eaten by the monster. Yeah, that's because they're basing it on fuses. We don't really use fuses anymore. We more use circuit breakers. But yeah, it's a safety device. And what happens is this fuse is between each of these wires. So you have, the electricity has to go through a fuse before it can get to the lights. We're going to talk about what fuses are on Friday's lesson. Sorry, no, we're not. We're gonna talk about what fuses are probably on Tuesday's lesson. Sorry, so that's another thing we're going to talk about later. But I guess the idea is just to sort of see this is how a circuit can be constructed. This is how a wire can exist. You guys might also begin to think that this is like, well, this is why you have 3 ports on your standard PowerPoint, because you've got one which is the active port, one which is the neutral port, which completes the circuit, and one emergency ground port, just in case things go wrong. We're going to talk about this in a little bit more detail next lesson. But yeah, the idea is we're going to talk about, but the idea is, again, active is like the positive, neutral is like the negative. It's like where these want to go, the current electricity wants to go afterwards. and G is like the ground. Now we have to be careful because we keep using the words active and neutral, but that's not actually the real deal. And we're going to talk about why that's not the real deal in a second. Oh, I'm running out of time. Here we go. Mains electricity is supplied to a home. The electricity is applied to our homes is called mains electricity. This is, by the way, an old meter, and this is a new meter. So you can sort of see these are what the meters used to look like. This is a digital meter. And then these will go through into something else. It's not when the electricity that goes through your walls, through your house, is actually an alternating current. It's not a direct current. It's not a direct current that keeps going, no matter what, it changes, it fluctuates. In Australia, the current changes direction every 1/100th of a second. So every 1/100th of a second, that's, 0.01. Or if it completes a full cycle every 0.002 seconds. So every 0.1 seconds is going forwards, backwards, forwards, backwards. It's doing that really quickly. It's going forwards and backwards 50 times a second. So it goes through those cycles extraordinarily quickly. Slow enough that you could probably hear the difference, but not slow enough that you could see the difference. It's very, 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 very quick, is what I'm trying to say. It has a frequency of 50 hertz, which means 50 hertz, by the way, a hertz, Hz, is just a fast way of saying per a second. And the other thing as well is that the voltage that runs through a house is about 230 volts in Australia. I had to look this up because I keep using the word 240, but 240 isn't wrong. The answer is just, it's better to say about 230 because, it can fluctuate. It can go as high as 240 volts in some areas because the voltage can fluctuate. The reason why we have such a high voltage, by the way, is because if we look at the voltage, the power that comes to your house is going to come in the power is P equals VI. Now, if we want to get the same power, we can use a high voltage or a high current. Now, in the wires that go to people's houses, so the big electrical wires, these wires that go to people's houses, they are actually have really high voltages, like 10,000 volts. The reason they have high voltages is because it's better to have a high voltage and a low current, rather than to have to run 240 volts, but to have 100, 10 amps or whatever it is. It's probably going to be 40, but I'm not going to do the actual maths here. It's better to do that than this scenario here. So why is it better to do a higher voltage? Because we also know P equals I squared R. The amount of power lost due to, resistance in the wires is linked to I squared R. So it makes sense to have a high voltage rather than having a high current. In other words, you give only a few electrons lots of energy rather than giving lots of electrons a little bit of energy. Because if you give lots of electrons a little bit of energy, if you try to push a high current through a small slot, you may instead lose more resistance and heat up the wire more. So that's why we have high voltages, 10,000 volts or something in those high wires. So that's why you really got to be careful around them. When it gets to the house, we dial it back. We dial it down to 230 volts, but then we crank up the current. But then it doesn't matter that we crank up the current because then we go and split the current anyway. So yeah, keep that in mind. So really quickly, a refresher in case you've forgotten. Direct current, or DC, is what batteries supply. they essentially make sure that the current goes in one way. It only goes one way, and that's how the light bulb is going to stay on, because the light bulb is going to continue to receive that same voltage. Electric current always flows the same way. Alternating current is a bit different. Alternating current is one which is constantly changing directions. So for AC, it goes one way, then it goes the other way, then it goes that way, then it goes the other way. The power of AC is that it constantly changes. Now you might think, oh, if it's constantly changing, surely the light bulb should go on and off really, really quickly. Technically it does. It does go on and off really, really quickly, but it does so quickly that you wouldn't notice anything. Especially with, especially because as well, if you think about it with a light bulb, you have to have, it has to take a little bit of time to turn off. So if you're turning it, changing the current every second, you're not really going to see it turn off unless you, because it's not going to get dim enough for you guys to notice that it's going to be turned off. So it just happens so quickly that we don't notice it. So AC current's the one we use in our house. You might be thinking, we're going to talk about why we use it in our house in a second. Is AC better than DC? AC and DC, it's hard to say which one's better. Someone asked really quickly. I think in some ways AC is better because you can have, there are some advantages to it, but ultimately all your electronic devices, when you start, AC is good for moving voltage and current around, but DC is good when it comes to dealing with individual circuits. You don't want to try and flood, because ultimately you want to make sure you've got a continuous voltage when you're dealing with it. So when we talk about like, oh, how does electricity work in the TV? You're going to use DC because there's so many components. It's going to get messy if you try and change the direction of all those components every second. And there's also just there's a lot you can do with AC that you can't do with DC. So yeah, they're good for different situations. Okay, this is going to be the last thing I'll talk about, and then I'll talk about this stuff later. So what does the AC current look like? This is going to be the last thing. The voltage of live terminals varies sinusoidally, which means sine wave. What that means is, and it cycles between 340 volts and negative 340 volts, taking 1/50th of a second or 0.02 seconds to complete a full cycle. So it goes from 325 volt positive, so going forward 325 volts, to negative 325 volts, going backwards in 0.02 seconds. So it does that really, really, really quickly. And we can see straight away here, we can see our sine wave. It's going up and then down and up and down. You guys, if you're worried about that, you're like, oh man, I really struggle with like understanding how those work in math. Don't worry, you don't actually need to know what a sine wave is. You just sort of need to know that it changes. What we're going to do next lesson, because we've run out of time this lesson, is I'm going to talk about these things, what the 0.02 seconds is, and 1/50th of a second as well. Okay, cool. I'm going to stop the lesson there. I'm going to, and then what I'm going to do is I'm going to get you guys, I'll talk about the rest of this stuff that I haven't talked about today next, which is a fair bit actually, but I'll talk about that on Friday. That's okay. And then we might on Friday, we should also talk briefly about how wires work in plugs as well. I should be able to talk about all that stuff in one lesson, but we'll see how we go. Anyway, that's it for today's lesson. I will see you guys next time. I've just realized, Tam, by the way, that this is going into period 4. So I might catch you at lunch and I'll send you something on your email. So just check your email and we'll deal with it then. Anyways, I will see you guys tomorrow.